The ratio test and more on the interval of convergence. Objectives. By the end of this lesson, you should be able to list the possible conclusions of the ratio test, apply the ratio test to a given series, use the ratio test to determine the radius of convergence of a power series, explain why we need to test the endpoints when using the ratio test to find the interval of convergence, and apply the geometric series test to a power series to find the interval of convergence. Alright, so let's take a look at the formal ratio test. What we need is the sum of a sub n to be an infinite series. And what we need to look at is the limit as n approaches infinity of this ratio. So the absolute value of a sub n plus 1 over a sub n. Now, if this infinite limit converges to a value less than 1, then the infinite series converges. But if this limit of this ratio, so the a sub n plus first term over the a sub nth term in absolute values, if that limit converges to a number greater than 1, then the series diverges. And if that limit converges to exactly 1, then the ratio test is inconclusive and doesn't tell us anything. The series could either converge or it could diverge. So what that means is we need to do more work and try another test to decide whether or not the series converges or diverges. So let's see the ratio test put into action. Alright, so in these examples we want to use the ratio test to determine whether the following series converge or diverge. So off to the right here, I'm going to write what we need to look at. We need to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And we need to compare that to 1. So whether it's less than, greater than, or equal to 1. So less than, greater than, or equal to is what we're trying to decide right now. So this series has a general term, an a sub n, of 1 over n factorial. So we need to set up the limit as n approaches infinity of the absolute value of, so a sub n, the general term goes on the bottom. So 1 over n factorial goes on the bottom. And what goes on the top is a sub n plus 1. So in other words, n plus 1 is going to be substituted into this n. So on top is 1 over n plus 1 factorial. Absolute value. Alright, so now we're going to do the limit as n approaches infinity. So right here, this is a fraction over a fraction. So instead of doing 1 over n plus 1 factorial over 1 over n, let's do 1 over n plus 1 factorial times n factorial over 1. Still in absolute value bars. So this is the limit as n approaches infinity of the absolute value of n factorial over n plus 1 factorial. Alright, let's think about this for a second. We want to try to figure out if this will somehow reduce. So let's plug in some numbers for a second just to get an intuition. What if I had 2 factorial, and the bottom, if I have n plus 1, well that would be 2 plus 1, so 2 factorial over 3 factorial. Well, 2 factorial is 1 times 2, and 3 factorial is 1 times 2 times 3. So what cancels out is the 1s and the 2s, and all I'm left with is 1 over 3. So similarly, the top part of this, and on this one example we'll go through showing all the steps here, the top of this is 1 times 2 times ... times n minus 1 times n, and the bottom part of this is 1 times 2 times n minus 1 times n plus 1. So in other words, everything on the top is going to cancel with almost everything on the bottom. The only thing left on the bottom is an n plus 1. And on the top, I'm just going to have a 1 left over. So what I'm really doing is evaluating the limit as n approaches infinity of 1 over n plus 1. So why did I drop the absolute value bars? Well, here I'm taking n values that approach infinity. So I'm only going to be plugging in here positive numbers. So the absolute value bars are a little bit redundant. So the limit as n approaches infinity of 1 over n plus 1 equals 0. Now, the ratio test says that if this converges to a number less than 1, then the original series converges. So converges by the ratio test. So it looks like a lot of work, but that's because we were going through the formal explanation of why this simplified down to 1 over n plus 1. So now let's take a look at the next example. And I'm actually going to go ahead and erase all this so we have room for the next example. Alright, so now I have the sum of n equals 1 to infinity of 3 to the n over n. Whoops, I don't want to write equals. That would have been a really bad thing to do. So this isn't equal to this limit. I'm just solving this limit to help use the ratio test. So I want to look at the limit as n approaches infinity of a sub n plus 1, so 3 to the n plus 1 over n plus 1 all over 3 to the n over n in giant absolute value bars. So now this is the same as the limit as n approaches infinity of 3 to the n plus 1 over n plus 1 times the reciprocal n over 3 to the n. And I'm going to go ahead and drop the absolute value bars at this step because everything here that we're talking about is going to be positive. And now I want to see if I can simplify things. So I am going to go through quite a bit of steps here just to justify everything. So this is the limit as n approaches infinity of 3 to the n plus 1 over 3 to the n times n over n plus 1. So all I did was switch the places of the denominators, which I can do because multiplication is commutative. Well, now the numerator is going to become 3 to the n times 3 to the 1, because if they have the same base, I can add their exponents. But the 3 to the n's are going to cancel out. So what I have left on the top, I have the limit as n approaches infinity. I have a 3 on top. I have an n on the top. The 3n on the bottom is gone, so I just have an n plus 1 on the bottom. So now this limit as n approaches infinity, and this limit at infinity, the degrees match, so my limit is 3. 3 is greater than 1, so by the ratio test, this original series way over here diverges. So now we've had an example of one where we're using the ratio test to determine convergence, and then this next example we have divergence. So now let's take a look at the third example. Alright, so I have the sum of n equals 1 to infinity of 1 over the square root of 2n. So I'm going to look at the limit as n approaches infinity of 1 over the square root of 2 times n plus 1. So remember, the a sub n plus first term over 1 over the square root of 2n. And we have absolute value bars around that quantity, which equals the limit as n approaches infinity. So when I multiply by the reciprocal here, this radical 2n is going to move to the top. And on the bottom, I have radical 2n plus 2. So I distributed that 2 inside. Alright, so here, if I think about this limit as n approaches infinity, well, this plus 2 here becomes pretty arbitrary once I start plugging in huge values for n. So the square root of 2n over the square root of 2n, well, that limit at infinity is going to go to 1. So in other words here, the ratio test is considered to be inconclusive. So I can't determine anything from the ratio test because the limit of a sub n plus 1 over a sub n gave me exactly 1, and that doesn't tell me anything. So this original series might converge, might diverge. There's not enough information to tell. So let's keep going. Alright, in this next example, I'm going to go ahead and set up my limit. The limit as n approaches infinity, and everywhere there's an n, I'm going to put an n plus 1. So the top is going to be n plus 1, and the bottom is going to be n plus 1 squared over n plus 1 squared. All that in absolute value bars. So now this is the limit as n approaches infinity, and I'll have n plus 1 over n plus 2 squared times, so that was the numerator, and then I'm going to do the reciprocal of the denominator, so n plus 1 squared over n. Alright, and so now at this step, we really have to try to think about what's going on with this limit at infinity. So on the top, I don't want to have to go through the process of doing a lot of expanding here, so I don't want to expand n plus 1 times n plus 1 and FOIL it all out. The key is to recognize that the dominating term up here, if I were to FOIL everything out, would be an n cubed. And similarly, in the denominator, n plus 2 squared, well, I would have an n squared from that multiplied by this n, so the bottom is also n cubed. So the ratio test in this example is also going to be inconclusive because this limit at infinity, if the degrees match and the leading coefficients match, the answer is just 1. So the ratio test is yet again, inconclusive. Can't tell what happens by using the ratio test. So now let's go ahead and look at another example. I have the sum of n equals 0 to infinity of the quantity 2n factorial. So we're going to do the limit as n approaches infinity of 2 times n plus 1 factorial over 2n factorial. And all of this in absolute value bars. So now I have the limit as n approaches infinity. On the top, I have 2n plus 2 factorial. So the 2 would distribute to both here over 2n factorial. And I'm dropping the absolute value bars because these quantities will be positive. So now the top is the limit as n approaches infinity. 2n plus 1 factorial, well, that would be 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, ... We're multiplying all out. So 2n plus 2 factorial would expand to this numerator. And then all over 2n times 2n minus 1 times 2n minus 2. So if we see what cancels out, the 2n and the 2n minus 1, and all of that part multiplied all the way down, these are all multiplied down, are all going to cancel with the entire denominator. So in other words, all that's left on the top is going to be, let's actually FOIL it out here, I'll get 4n squared plus 6n plus 2. So as n approaches infinity, this quadratic is going to go to infinity, which is definitely greater than 1. So by the ratio test, this series, this series diverges. But was this the most efficient test to use? So because we're going to start building on our tests, it's important to first try the nth term test on any series that we don't automatically recognize to be geometric or telescoping. So if we would have done the limit as n approaches infinity of the general term, 2n factorial, well, this clearly is going to go to infinity. So remember, if this thing doesn't go to 0, then the original series definitely diverges. So this would have been the shortest method to determine divergence, although using the ratio test did also work to conclude that this sum does go to infinity. So the ratio test concluded that the sum diverges. And let's take a look at one final example where we apply the ratio test. So we have the limit as n approaches infinity of 2 to the n plus 1 over n plus 1 factorial. And here's what I'm going to do. I'm going to jump to writing multiply by the reciprocal already. So hopefully we'll get to that point where we don't actually have to do a sub n plus 1 over a sub n. We can do a sub n plus 1 times the reciprocal because most of our general terms are going to be fractions. So this would technically be in my absolute value bars. So now, how this is going to simplify, the limit as n approaches infinity, well, 2n plus 1, that's 2n times 2. So the 2n's will cancel. So in the numerator, all I have left is a 2 from these two parts. And now n factorial over n plus 1 factorial, Well, we decided that the only thing left over was going to be an n plus 1, and that's going to happen in the denominator. So as n values approach infinity, the bottom of this is growing bigger, so this limit goes to 0, which is less than 1, so the original series converges by the ratio test. So these are just a few examples of applying the ratio test to a series. It tends to be a lot of students' favorite test to try, although what that previous example does say that we should get in the habit of doing the nth term test first, but doing the nth term test here would have given us inconclusive, because factorials, as you know, do grow faster than exponentials, so this limit of the general term would have been 0 and wouldn't have told us anything. So in this particular example, we would have had to use the ratio test. Alright, let's start by talking about steps for finding the interval of convergence. So we're trying to find the interval convergence of a power series. So here's a general power series representation. So c sub n times x minus a to the n. Well, if c sub n is a constant, so if c sub n actually happens to be just a number, then we're going to apply the geometric series test to find the complete interval of convergence. That's the best possible scenario. But if c sub n is a function of n, we're going to apply the ratio test to find an incomplete interval of convergence. So it's incomplete because we have to test the endpoints of convergence to then make it a complete interval of convergence. So we're going to see examples of both of these in our attempts to find a complete interval of convergence in both situations. Alright, so in this first example, we want to find the interval of convergence where the sum of n equals 0 to infinity of -2 times the quantity x plus 5 to the n. So the first step is to recognize that this is of the form the sum of n equals 0 to infinity of c sub n times x minus -5 to the n. So this is a general power series where my center value is -5 and my c sub n is this constant function -2. So in fact, this is a geometric series. And if we think about it for a second, if I plug in any x value here, it is going to look geometric. So let's just plug in x equals 0 just to confirm it. So if I let x equal 0, this is the sum of n equals 0 to infinity of -2 times 5 to the n. So this is definitely a geometric series, and this geometric series does not converge because 5 is greater than 1. So 5 is definitely not in my interval of convergence, but I want to find out specifically what it is. And here's what we need to remember is that this is of the form a r to the n. So if I want to find what x values this geometric power series converges to, I'm going to take this inside quantity, this x plus 5. So I need the absolute value of that inside quantity, x plus 5. In order for this thing to converge, this quantity has to be less than 1. So if I want to solve this, the way that I solve this inequality is if I have the absolute value less than 1, I'm going to stick the positive quantity, x plus 5, between 1 and -1. So this is a review of pre-calculus a little bit, solving absolute value inequalities. And now I'm going to go ahead and subtract 5 from both sides of the inequality so that I can get x by itself. So -1 minus 5 is -6 is less than x is less than 1 minus 5 is -4. So we just found the entire interval of convergence to be from -6 to -4. So let's try to think about that for a second. My center was -5. So if I'm thinking about an x-axis, my center value was -5. So I know that the only values that this power series converges for are between -6 and -4. And there would be open parentheses at each of those endpoints. So based on this graph, I can also determine my radius of convergence would equal 1. So if I'm given the interval of convergence, I can also find the radius of convergence. So there's actually no need to graph it either. What I can do is I can just take these values, I can subtract one from the other and divide by 2. So -4 minus -6, so take the bigger one and subtract the smaller one, and then divide by 2. So here I'll add the opposite. So 2 divided by 2 gave me a radius of 1. So because this is geometric, I can say with certainty that this interval from -6 to -4, those are the only x values that are going to allow this original series to converge. So the endpoints will not work because the geometric series test says that the absolute value of r has to be less than 1, and that converges. Now, if the absolute value of r is greater than or equal to 1, then both diverge. So that's why the geometric series test is nice. Alright, so let's do one more example where this power series is geometric. So find the radius of convergence for the sum of n equals 0 to infinity of x minus 3 over 2 all raised to the n. So the key here in recognizing that we can apply the geometric series test is that that constant value, or that c sub n value, is constant. So there's really that 1 here. So in other words, the only way this thing can converge is if r, so this whole quantity here is r, if the absolute value of r is less than 1. So I'm going to take the absolute value of x minus 3 over 2 and solve for what x values allow this quantity to be less than 1. So properties of absolute values tell me I can take the absolute value of the top over the absolute value of the bottom. Well, the absolute value of 2 is 2, so this is really x minus 3 in absolute value bars over 2. That has to be less than 1. So now let's multiply both sides by 2. So these will cancel, and x minus 3 in absolute value bars has to be less than 2. So again, solving an absolute value inequality, we're going to take the inside, x minus 3, and put it between -2 and +2. And we're going to add 3 to both sides. So this left side is 1 is less than x is less than 5. So what I found right now was my interval of convergence that I'll abbreviate IOC. So my interval of convergence is from 1 to 5. So if I want to find the radius of convergence, that means I'm going to take 5 minus 1. So the radius of convergence is going to be 5 minus 1 divided by 2. So that's 4 over 2, which equals 2. And that implies that the center of this power series is 3. So we can see that from the original problem, we have the x minus a, my a value is 3. So if 3 is the x on the x-axis as the center, then this power series converges from 1 to 5. So we need that equal distance of the radius on both sides, and that radius is 2. So my radius of convergence, r equals 2. Alright, in this next example, we want to find the radius of convergence for the sum of n equals 1 to infinity of n over 2 to the n times x minus 3 to the n minus 1. And then, can we find the interval of convergence? So this is an example where c sub n is not a constant. So n over 2 to the n is not a constant. And then this is x minus 3 to the n minus 1. So this is of the right form because my index starts at 1. So that's why my exponent here is to the n minus 1. So to find the radius of convergence, I want to try to find the interval of convergence, and we'll see what happens. Now, this isn't geometric, so I have to try to apply the ratio test, and it's going to get really long and a little ugly, so we want to stay as neat as possible. So the ratio test says that the limit as n approaches infinity of the absolute value of a sub n plus 1. So everywhere I see an n in this general term, I'm going to put an n plus 1. So n plus 1 over 2 to the n plus 1 times x minus 3 to the n plus 1 minus 1. So this whole thing is a sub n plus 1. So all over a sub n. So n over 2 to the n times x minus 3 to the n minus 1. Alright, so now I'm going to go ahead and rewrite this, the limit as n approaches infinity. So first I'm just going to take a look at these two portions here. So I have a fraction over a fraction there, so I'm going to rewrite that as n plus 1 over 2 to the n plus 1 times the reciprocal of n over 2 to the n, so 2 to the n over n. And then I'm just going to go ahead and leave the x minus 3. So x minus 3 to the n on top, because the plus 1 minus 1 cancel. And on the bottom, I have x minus 3 to the n minus 1. Alright, so all of this is in absolute value bars. And here's something that's a little different. I'm applying the ratio test, but I'm applying it in a specific way because I want to know, or I want to guarantee that this limit is about to converge to a value less than 1. So if I want the interval of convergence, the ratio test tells me that this series converges whenever the ratio a sub n plus 1 over a sub n, when that limit of that ratio is less than 1. So I'm really solving this. So I have to do a lot more simplifying, though, to actually get it down to something that I can solve, some inequality I can solve. So this 2 to the n plus 1 is 2 to the n times 2. So this 2 to the n and this 2 to the n will cancel. And then here I have x minus 3 to the n, and then this is x minus 3 to the n minus 1. So in other words, there's one less copy of x minus 3 on the bottom. So let me just try to justify that. If I had, let's say, x minus 3 squared over x minus 3, so there's 2 copies of x minus 3 on the top and 1 copy on the bottom, the only thing that will be left is 1 copy on the top. So this whole thing cancels, and this n cancels and becomes a 1. So now let's try to see what I have left. So this is the limit as n approaches infinity of, let's see, I have an n plus 1 on top, and on the bottom I have the 2 and the n, so 2n times x minus 3 to the 1. This has to be less than 1. So now let's evaluate the limit part. So the limit as n approaches infinity, well, the only n's, let's change colors, so as n approaches infinity, the only n's are here and here. So it's like I'm taking the limit as n approaches infinity of this portion, because this has x's, this is not affected at all by this limit. So since these degrees match, this portion right here, n plus 1 over 2n, is going to become 1 over 2. And so now we're going to drop the limit because we've evaluated it. So I have 1 over 2 times x minus 3 in absolute value bars is less than 1. Alright, so now this is something that I can solve. So I'll scroll down, make a little bit more space. So here, let's see, this is the same as 1/2 times x minus 3 is less than 1. So my properties of absolute values tell me that I can pull out this 1/2 because it's positive, and then multiply both sides by 2. So these will cancel. I'll get x minus 3 is less than 2. So negative 2 is less than x minus 3 is less than 2. I'll add 3 everywhere. So I'll get 1 is less than x is less than 5. Okay, that was a lot of work. What did we just find? Did we find the interval of convergence? We did not, or maybe. That's really the answer here is maybe. So let's go ahead and scroll up a little bit. We were asked to find the radius of convergence, and then can we find the interval of convergence? So let's talk about the ratio test for a second. I know that the limit of a sub n, or a sub n plus 1 over a sub n, when that limit as n approaches infinity is less than 1, well, then I know that all of those values are going to make my original power series converge. So everything between 1 and 5 is going to be part of the interval of convergence. But let's remember the ratio, what the ratio test says when x equals 1. So when x equals 1, we're inconclusive. So what I know so far is that my possibilities for the interval of convergence are 1 to 5, so not including the endpoints, closed 1, open at 5, or open 1, closed at 5. So in other words, I'm not sure what happens at the endpoints. Or, I guess technically, sorry, the last possibility, close 1, close 5. So these are the 4 possibilities for the interval of convergence, and I won't know until I test them. So until I go ahead and take 1 and 5 and plug them back into the original power series and see whether or not that series converges or diverges. So that's why we're going to need a bigger collection of tests to determine whether or not the power series converges at specific points. Which points? At the endpoints. So these are the possibilities for the interval of convergence, but I do have enough information to find the radius of convergence. If the interval of convergence goes from 1 to 5, so that's a length of 4, then the radius is going to be half of that. So my radius of convergence, let's write that down, the radius of convergence r is going to equal 2. So that came from 5 minus 1 over 2, so that's 4 over 2. So I get out 2. So this I know for sure. Possibilities for interval of convergence are of these 4, and I can't tell until I plug 1 and 5 back in up here. So just to get an idea of what that would look like, I'd have to plug 1 and 5 into these x's. So in other words, does the sum of n equals 1 to infinity of n over 2n times, so if I plug in 1 here, 1 minus 3 is negative 2 to the n minus 1. So does this thing converge? If we can show this, so this only has n's in it, so if we can use a test to show that this converges, then that means 1 is in the interval of convergence, and I could put a closed bracket around 1. And then I'd have to do the same thing with 5. So if I plugged in 5 for this x right here, 5 minus 3 is 2, so I'd also have to check whether this series converges or diverges. Alright, let's do one more example where we use the ratio test. Find the radius of convergence for the series n equals 0 to infinity of x minus 2 to the n over 2n. And then can we find the interval of convergence? So the sum of n equals 0 to infinity, I'm going to rewrite this as 1 over 2n times x minus 2 to the n. So I can see that my c sub n term is a function of n, not a constant, so I do have to apply the ratio test. So what I need to happen is I need the limit as n approaches infinity of the absolute value of a sub n plus 1. So 1 over 2 times n plus 1 times x minus 2 to the n plus 1 all over 1 over 2n x minus 2 to the n. I need this to be less than 1. So let's simplify now. I'm going to end up getting the limit as n approaches infinity of, let's see, 1 over 2 to the 2 times n plus 1 is 1 over 2n plus 2 over 1 over 2n. And then let's go ahead and simplify this in one step. So I have x minus 2 to the n plus 1 over x minus 2 to the n. So this will cancel, and I will only have one copy of x minus 2 on the top. So I have x minus 2 to the 1 left. That needs to be less than 1. So I'm running out of space. I'm going to bring my work up here. The limit as n approaches infinity of the absolute value of, if I multiply by the reciprocal here, so times 2n over 1, I'm going to get 2n over 2n plus 2 times x minus 2, that has to be less than 1. So now let's evaluate my limit. As n goes to infinity, I'm only affecting this portion here with n's. So at n goes to infinity, the powers match and the leading coefficients match, so this portion here becomes a 1. So I'm going to go ahead and drop the limit, and this is really just x minus 2 is less than 1. So negative 1 is less than x minus 2 is less than 1. And if I add 2 to all pieces, I'll get 1 is less than x is less than 3. So again, I don't know what the interval of convergence is. Can we find the interval of convergence? Not unless we test the endpoint. So there's too many possibilities, but the radius of convergence is going to be, so r is going to be 3 minus 1 over 2. So that's 2 over 2. So my radius of convergence is 1. But my possibilities for the interval of convergence are 1 to 3, closed 1, open 3, open 1, closed 3, or closed 1, closed 3. We're not sure. We'd have to go back and plug 1 and 3 into this original x and then try to solve that infinite series.